now and give a brother room. To the ladder, instruction. Boom! Don't back up now and give a brother room. The fuse is lit and I'm about to go boom!
Okay, in the previous lecture we dealt with the idea that reactions are concentration dependent. We have reaction orders. We talked about how we could solve for those, the overall reaction order, and we went through how to solve for the rate constant at a given temperature. Well, now we need to actually look at the rest of the picture, and that is how difficult is this reaction actually to perform? And the rate constant is the only way of actually giving us that picture because it's related through the Arrhenius equation to the activation energy. So that's its relationship to temperature. If we look at the energy diagram, the simple version is we're looking at not delta H, which is the energetic payoff once the reaction has gone, but we're more interested in the energy of activation, which is how high is the hill we have to climb to get the reaction to go. Much more useful information, but not quite so easy to get at. One way to look at this is by thinking that if the molecules are actually colliding hard enough, we'll actually see a reaction happen. So again, we're sort of falling back to kinetic molecular theory for a moment, but here's what that might look like.
Hey, buddy.
Whoa! You know you can't bring that weak-ass stuff up in this Humpty Bumpy. You killed a Joe, you make some more!
This is the legendary Arrhenius equation, the relationship between the rate constant and the energy of activation and temperature. However, if you're looking at it, you might notice a problem with it. And that is that we've taken a one-variable problem, the rate constant, and now made it into a three-variable problem, the rate constant, the Arrhenius constant, which we don't know anything about yet, and the energy of activation, which we also don't know anything about. So we've taken a simple equation and made it much more difficult.
That's great psychology. Why don't you just say something bad about my mother?
Your mama is so ugly.
Look, you make this run.
Okay, so maybe that type of psychology doesn't actually help us, but we can actually deal with this in very much the same way that we did the rate equations when we had so many variables there, and that is we can look at two different points, and that will help us get rid of some of the variables because they won't vary. We'll hold them constant. So if we look at the Arrhenius equation as two separate points, which in this case would mean solving for the rate constant under two separate temperatures with all of the other concentrations held constant, and the Arrhenius constant, the A in this equation, does not change with temperature, so that also will be a constant. So if we look at that as a ratio of 2 points, we actually can cancel out a lot of this unwanted variables. We still have 2K values, we still have the energy of activation, we still have 2T values which we can measure, but the Arrhenius constant is gone. So it allows us to relate basically K and temperature, two things we can measure and calculate, and be left only with a solution for the energy of activation. Well, that still leaves us with a bit of a mess mathematically because we're looking at the term we're interested in, the energy of activation, being an exponential term to E and the ratio between my rate constants on the other side of the equation. So I have to pull a little bit back out of my mathematical trick bag again, and that is to use a natural log to help us remove the E factor here. Now this is the point where mathematically people have some trouble. I suggest strongly that you practice this. As I warned you when we talked about heat of vaporization, there are a number of different relationships in chemistry in this course that are natural log relationships on one side and invert temperatures on the other side. Here's another one. But you'll look at it and realize it's very similar. We're talking about an energy term here, E of A, instead of the heat of vaporization that we did for pure physical properties, but otherwise this is very similar. We can use rate constants here, but since we're holding all the concentrations consistent, then we could also get away with actually using the rates themselves. What that means is that if we, for instance, had a rate that we knew doubled, that rate 2 is twice what rate 1 was, it also means, since everything concentration-wise is being held constant, that K2 is twice the value of K1. So we can look at rate ratios. The Arrhenius equation in its strict form is rate constant ratios, but they mean exactly the same thing. So here's a very typical example. You're given a reaction, you're given a set of temperatures, in this case only 2, and you're given either the rates at those temperatures or the rate constants at those temperatures, as you see in the table here on the left. Do we need to solve for the reaction orders? No. Doesn't matter, because as long as the concentrations are being held consistent and constant, then they don't matter. They will all cancel out. X squared over x squared cancels. X to the third over x to the third cancels. Doesn't matter what the reaction order is. So we can do this and actually work out the activation energy of a reaction with no other information than 2 temperatures and 2 rate constants. So if we take those values for the Ks, put them into the left side of the equation, we take the temperatures, making sure they're in Kelvin. In this case they are. In many cases in the literature or your practice problems they won't be. Make sure they're in Kelvin, put them in as inverted on the right side, and remember this one. This is one I catch people with every semester. The R value is in joules, so you have to convert that to kilojoules. Now I have it written here as 8.31 times 10 to the minus third. That's converting it to kilojoules per mole Kelvin. Make sure you do that. Energy of activation, along with other enthalpy terms, delta H, are written in kilojoule terms most commonly because joule terms are too small. The only thing that's consistently written in joules is entropy, which we will deal with near the end of this course. So we put all of that in place, and assuming that we actually don't make any math errors along the way, we can actually work our way through this, get to an energy of activation of 103.4 kilojoules per mole. Now, be aware of this. Most reactions, the energy of activation is going to range anywhere from 25 up to about 200. If you start seeing numbers that are like 10,000, you probably lost the 1,000 conversion to kilojoules from R. You see numbers that are like 0.1 kilojoules, same thing. You did something wrong with a decimal place somewhere, because those are impossible reaction-wise. Nothing is that easy, and nothing that we're going to deal with ever is that hard. So realize those numbers should be, reasonable numbers, instead of extremely tiny or extremely large as values for energy of activation when you're over, when the problem is over, and you probably did it right. And of course, energy of activation is the energy of the going uphill, so it has to be a positive number. You're putting energy in to get over that hump, not getting the energy out, which you may or may not get back if delta H is exothermic or if it's endothermic.